Ooh, wow. Okay, so let's see if I can remind you what we are doing and where we're going and where we are. Very sorry for coming so late. So, okay, so recall, we wanted to get a dense ideal on omega 1 with CH by forcing over the terminus. Yeah, so the goal was prove the following theorem of Witten. Oh, the theorem says is due to Witten. So assume ADR state is regular plus V, oops, plus V equals L. So it's constructed from the power set of reals, right? Okay, so we want to force with, let P be collapse omega 1 R times add one coin subset to omega 2, right? So then VP satisfies CH plus there is a dense ideal, omega 1 dense ideal. There is an omega 1 dense ideal on omega 1. Okay, so the way we should think of dense ideals, so if I is dense, is omega 1 dense, so if you have an omega 1 dense ideal, what happens is the generic embedding is induced by the collapse. Then if U is the generic ultra filter, a generic ultra filter, or let me see, then for all, whenever G collapse omega R is generic over V, right? There is a generic U PI. So PI is the forcing, you force with positive sets, right? So it's the forcing that will add an ideal on omega 1, ultra filter to omega on omega 1. And the conditions are the positive sets. Ordering is, of course, subset, right? Then there is a generic U in VG and Uya sometimes, and into V. So basically, the way you want to think of this is that the generic embedding is added by in fact, more is true, but this is a little bit harder to prove. In fact, PI is forcing equivalent to collapse, sorry, call omega, yeah, R, omega 1, I should say. That should be omega. It should be omega 1 here. Here too should be omega 1. Okay, so you have a dense ideal, then the generic is given to you by just collapsing omega 1 to be countable. And this type of embeddings where you collapse, so it's an ideal, but you're collapsing omega 1 to omega and you're getting a generic embedding. This type of things are usually happening when you have when you get your ideal after collapsing a measurable or some large cardinal. So you make your large cardinal to be omega 1, then you might be able to get such an embedding. But usually, if you look at the standard proof, the standard proof for getting a precipitous ideal from measurable, you don't just collapse kappa, you collapse something more, right? So that forcing would collapse kappa plus, for example, because you need to take the, you basically need to collapse J kappa. Okay, so here we're just collapsing. The way you should think of it is this universe looks like some large cardinal was collapsed to omega 1, and then you collapse omega 1 to omega and you get your generic. Okay, okay, so from large cardinal intuitions, this would seem like you're collapsing something like a huge cardinal. But we are forcing it over model of ADR plus this plus data is regular. That's way below a huge cardinal. Yeah. So that is that. Okay. And so we've done basically all our homework. I don't know if you guys remember. By homework, I mean all the background material, but I don't know if you remember. So why don't I review it? So let's see. So the first thing is, first, there's the Solovay theorem, which we proved, right? So this says ADR implies that the Lab filter on the omega 1 of R is an ultrafilter. So this was, so let mu with this ultrafilter. Okay, so the club filter on P omega 1 of R is an ultrafilter. Okay, that's the very first thing we did. The other thing that I would like you to remember is we call under AD, the union of well-ordered union of meager sets of reals, right? Is meager. And it doesn't matter how long the length of your well-ordered set of meager sets is. You can take as many as you want. As long as it's well-ordered, the union will be meager. Okay, so that was the other important thing. Now we had this interesting ideal on set of reals. So the ideal of weakly, I guess the filter, the way I'm going to set it up, it will be filter, not an ideal. And maybe these are just the positive sets. Well, just only the subsets of no, these are positive sets. I should call it the ideal because I'm doing it over below condition, so there will be ideal. We have weakly meager meager. Okay, but the one we need, so I will just tell you what the positive sets are. Yeah. So given A r to the omega and a condition P in called omega r, we said we wanted to define what it means for this A to be weakly comeager below P. Okay, or you could say weakly meager, right? So what I will have it the positive set. So the I positive, what I'm defining is the are the I positive sets. So we say A is weakly comeager below P, right? So this sounds like a large set, but it's large below P. Okay, what are we gonna do? We want to bring it, basically the idea is we're gonna relate the collapse forcing with Solovey's measure. So Solovey's measure was talking about club of countable sets of reals. Here we're looking at countable sequences of reals. So what is the connection between sequences of reals and sets of reals? Well, the range of a sequence is a set of reals, right? So if you have a sequence of reals, then this range is the set of reals. Okay, well, we want to say that the sequence you have is a generic sequence, not just an arbitrary sequence. Okay, so we say A is weakly comeager below P if there is a club C, which is a subset of P omega 1 of R. Right, so these are sets of countable sequences, countable sets of reals. So, right, so here there are no enumerations, such that for all sigma in C, if I look at the so for all sigma in C, with on the P, the condition, so the image of P is a subset of sigma, and 2 for omega many G, right? For omega many G, A intersection A intersection sigma to the omega. Oh, I didn't need to say for omega many G. Yeah, I didn't need to say. I want to say that the A intersection sigma to the omega A intersection sigma to the omega intersection NP is omega in NP. And you don't want to say this. Okay, so what is NP? NP is the open set, right? Sigma to the omega is a Baire space, and NP is the set of all sequences that contain P as its initial segment. And you want to say that A contains omega many of those. Okay, but omega means that omega many, right? Because there's a set of generics is also omega. So you could also equivalently say the way I was writing that the set of generics, there's a omega many generics in A. Right. So this was the ideal we looked at.
Do you want omega in NP or in NP intersect sigma to the omega? Or is that equivalent?
Well,
NP is contained in sigma to the omega because
not really. It depends what one
no,
means
depends
by
in what space. Yeah, depends in what space.
Yes. But if you intersect with sigma to the omega in the first line, then
yeah. Yes. Okay. Now so we have Yoko came back. So suppose now we have so the other thing I want to remind you is that now suppose now G is a whole omega R generic, right? Then U R to the omega, there exists P in G. A is weakly omega. Or below P. Is an ultra filter. I mean, we've shown this, right? So let me say we have shown. And moreover, we've shown that if you take this ultrafilter, then and this was also very important, and the embedding, the ultra power embedding restricted to the ordinals is the same as pi mu. So mu was the club filter restricted to the ultra power of the ordinals. So this had the consequence that that the ultra power of V by U is well founded. Okay, so that already gives us an idea on something.
Sorry, Rigor, can you remind where does well-foundedness follow from?
Because pi mu is a countably complete. What does it mean to be ill-founded? It means that.
Oh, and this the countable completeness was the Soloviev kind of dovetailing
Yes.
argument. Okay.
Right. So I don't know if it actually. Well, I mean, the way I wrote it, so we proved something more technical, right? I don't know if you remember, we actually proved that if you have a function which represents an ordinal in the U ultra power, then you can find an equivalent function in the mu ultra power that agrees with that representation. So there was that a more technical version of this, which we don't need to recall. But if you write that the pi mu U restricted to ordinals is the same as pi mu restricted to ordinals, then that tells you that the ordinals have to be well founded. Yeah, right. Because the embedding on ordinals is well founded, but then that's what it was. Okay, so the other thing that we proved, which was important, so also we have shown that it's actually, if you do the pi mu ultra power and look at where omega 1 goes, that will go to theta. Okay, so what this means, it's very interesting what's happening, because so now why mu is, wait a second, what happens? So I should make my now 2, right? So why was this important? Well, because theta, this is important. Because theta is omega 2 in this VP. Right, so remember, P was the forcing of the first enumerator reals of length omega 1, and then you add the coin subset to omega 2. Auto is here. And we've shown that this is true. Okay, so what it means, right? So I u omega 1 is equal to omega 2 in VP. Okay, so this is important. Okay, so the other thing that we discussed, and we will be using that today, is this thing. So finally,
Omega 1 was the same everywhere because P was a countably closed passing, right?
Yes.
Yeah, okay. Or two countably closed passing.
So finally, we've shown that so ADR implies that if Q is a poset of size R, so that means there's a surjection from R onto Q, right? Then every set of reals is QUB, meaning if you force with Q, then you have a natural extension. Or every set so this means that, so let me remind you what this means, i.e. There is a pair of trees, yes, such that one projection of T is A, and two, for all V generic, VH thinks that projection of T is reals minus projection of S. Now, there's a stronger version of this that's true. Moreover, which follows from this version, because you can apply this version to A sharp, right? So moreover, ADR implies that if Q is a poset of size R, then for any A and for any generic, there exists J from LAR into LAGRG. So AG is what is AG? AG is projection of T in which and RG for reals. Something even more is true, a little bit stronger version of this. Actually, maybe seemingly stronger, but it probably is exactly equivalent to this. So another version, and write another version because I'm pretty sure it's formally equivalent. Another version which we would use. Suppose N or A is a set of reals, and alpha is less than theta. and such that, yeah, okay, let's say such that it doesn't have to be model of CF, but let's say L alpha AR is a model of ZF or some nice fragment. Okay, it doesn't have to be CF. Okay, so because alpha is less than theta, I have a function from reals onto L alpha AR surjection. Right, so if you take such a surjection, then you can push the supercompactness measure, the Solvay measure onto this, right? Now set n to be L alpha AR and mu n to be the Clap filter on n, the supercompactness ultrafilter on n, which we get by, you can use this F, so use F to push mu, basically. Okay, so now we can take countable elementary substructures of n, right? So they measure one many, mu n measure one many such elementary substructures, and you can force over them. Turns out you can embed it back. So suppose I probably wanted to take this exactly the same A. Yeah, okay. So let Q in N be such that N thinks cardinality of R is equal to cardinality of Q. Right, so I take a pole set of size reals, then for club of X, child elementary in N, countable. If NX is the clubs, transitive clubs. If NX is the transitive clubs of X and phi X and X into N is the inverse. And G which is the inverse of Q, is NX generic, then there is J from L, oof, L alpha X into alpha AR. So step and A from L AX RX into L such that IX is equal to K circle, oh, sorry, J circle Okay, well, that was long. Basically, if you take a countable hole and you did the forcing, then you can realize the model pickup, right? Let me draw a picture. It's saying something very simple. You have L alpha AR. We collapse this to LAX RX alpha X. Then we did the forcing. So we went to L alpha X AX RX G, right? Now in this model, I'm evaluating the version of AX and the reals, right? So there is a model contained here, which is the L alpha X AX G RX G. So there is this embedding K. That embedding we already had. I already said that there is always an embedding like that. And then we have this other embedding. So this is pi x, this is K, and this is J. Okay, so if you take a hole, go to the extension, generic extension, then the version of the model you have embeds back up in a way that the triangle commutes. Okay, so this is even stronger thinking.
Do you
Ooh. Yeah,
what was pi x, or what was x? Sorry, the
X was an elementary substructure of. Okay, the way I wrote it is a bit mysterious because
Of
I
what?
should have really taken A sharp and then do it for A.
Yes,
Pi x was
that's what I was thinking. You need to have a sharp still, right, to get the k.
well, you don't really need, because you could always assume that your X is also an elementary. You don't really need it, but it's more clear to say it that way. So X is an elementary substructure of N, but there is a club of, the way you would prove it is you would work with N sharp. So to prove, do work with, I'm not saying K is inside the model. To prove it, work
Yeah,
with,
okay. I think I understand. Just
yeah,
saying that for many x's this works, right?
yes, yeah, that's all I said. And then yeah, right. So I don't know if I should I explain why? Okay, to prove it,
If
let
you
me just
said
write it. Yeah?
something like for club axis, it works, but what does it mean here?
For club of X.
For club many axes.
Yeah, that means that there is basically club means here. Okay, so let me say what club means here. Oh yeah. So
Closed and cofinal subset of the space of countable subsets of the thing.
you but you wanna take a function is a club if there is a function such that C equals set of X in P omega 1 of N. So countable such that fx is a subset of X.
But this is the same as the literally closed and cofinal, right?
Yeah.
I mean,
Well,
so
yeah.
this is a subset. You can find a subset which has this, like these sets generate the full club filter.
But is it the same without choice though?
I think in this context,
I think F is stronger, right?
I see.
but in this context, you can prove that it would agree because you can always force choice in some nice way. So, but this is the definition we usually take. Right? In this one. But okay, so how would you prove the theorem? Let me just say it, right? Not write it. I'm not saying K exists inside L alpha x ax. I'm not in the generic extension, just saying that k exists. So how would you get k? Well, you would go to A sharp and then apply the theorem that we know about A inside A sharp, right? So we know that there is this k, but k only exists in a slightly larger universe. Okay, and then you get the rest basically.
Grigor, why does k exist in sharp simply? Because like the being extend, being UB seems to be a stronger property, like M1 sharp of A or something like this,
Okay,
right?
maybe you just go to some bigger universe in which you see that A is universally bare, right? So go to the
Okay.
universe in which there is a set of reals and things
Okay,
that A is
Okay, but sharp in general is probably too weak, right? Like it's
yeah, it depends what A is, but it might not work for A sharp. Yeah, so you just go to slightly larger universe, and then what you have to see is that if you now take any elementary substructure of the slightly larger universe for which it works, right? Its restriction to n is also elementary in n. So that's how you get club of elementary substructures of n. Okay, I mean, it might have been better to write it with A's if with slightly larger models, right? Okay, so this is what it is. Okay, so we want to prove probably now the first main thing for us to prove. So what we want to prove next?
Sorry, I was still confused. Why do you need this? Why do you need here to push forward the measure? You said something you want to push forward the
No,
measure.
I'm just meant what the supercompactness, what I mean by take the supercompactness measure. So we need to know that there is an ultrafilter. Oh, you mean it works no matter what?
Yeah, I mean the thing you just proved,
Right. Yeah, you don't
because the
need
push
this
forward,
club,
the push forward could go wrong, right? If your F concentrates, like if the pre-image of something is large.
No, but it's the club filter, so it will not. There's only one supercompactness measure. So and it's normal, so it will contain the clubs.
No, but I think but my question is, can the, if you push forward with a bad F, can it not become a principal filter? Like the F should be like small, like have small pre-images or something.
Why would it be principal? It's you say something is measure one if it's inverse as measure one.
So what if there's some point in the image that's hit very often? If it has a large pre-image, some point, then you have a principal alter filter, no? Usually to push forward you need, and to still get something non-trivial, you need that each pre-image is small. I think it's a little different here because you don't have a filter on R, do you? Or do you have a filter on R or R to the omega on countable subset?
Yeah, R to the omega. I think that's the thing.
But still, could it not happen that like just some very large subset of R is mapped to, maybe not. What is the no, sorry, no, because it's the club filter, yeah. And the club.
Yeah, but what sounds like you need a bijection. Yeah.
It's, yeah.
No, I think you need the bijection, right? Because, or I I mean, what if I take an X and then too many, so.
I'm actually not even sure at what point you used this push forward argument. In the
No,
argument,
but
you didn't use it,
we
right?
need, but we will use it. We need to know, just a second, okay? I mean. Yeah, if I take some, if everything is mapped to, that would not be very good. So what are we supposed to do? Well,
But is it's not possible that everything is mapped to one point, right? And to get a club in the pre-image, you still need to have I mean, all reals need to show up.
yes, but what is the definition of the ultra filter? I mean, you say some countable, some set is measure one if what? If,
Yeah, I mean, you take the pre-image point-wise, and then you look at all the omega sequences through those. I don't. It's not clear that it's an ultra filter, I guess, or that like
but
complements one.
it's, why are the things countable? That's, I was just too tired at the moment. I mean, if I take it, what is the push for inverse? So you take F inverse, there's the countable sequences there, right? What is F inverse sigma? What a countable set? So you have some countable subset of this N. What is F inverse of that?
No, I mean you have.
Oh no! So we
F
take all the countable sigmas.
Yes.
Such that F pointwise image sigma. Yeah. So
Yes.
But then that works, right? It's fine.
I think it works. I mean, should work.
Yeah.
But where do you use it in this proof? Because I thought that.
Not in this proof. In the next proof
Okay.
we will use.
Okay, sorry.
Yeah, so we have. Where was I? Oh, yeah. So the next thing is basically the first thing that we want to do. Next, we want to prove that basically want to that the in and if G is generic for P, then in VG we have that that the NS on P omega 1R is presaturated. The precipitous. So I want to, I'm not gonna, we will prove something stronger next time. SCP does SCP. And we're gonna do this by, like the way we usually do it. We will take a function that's supposed to represent, precipitous means the ultra power is well founded, right? So NS means the ideal of non-stationary sets. Precipitous means that the ultra power is well founded. And we usually do it the way we've done in the previous case when we've shown that the ultra power is well founded by this U. We'll take a function that represents an ordinal and we'll find another one on this mu ultra in the mu space, the one by the solar wave measure, and show that they represent the same ordinal. Okay, so for this strategy to succeed, I need to know exactly what sets are, how the sets which are stationary or contain a club in VG are related to the ground model sets. What is the connection between the V sets which are which are stationary or contain a club, right? And the sets somehow how can you characterize those sets within the ground model? And that's the sort of the key lemma of this whole thing. One thing that you should pay attention to is that this object is the same. Yeah. So notice that P omega 1 R of Vg, because P was countably close poset, is the same as P omega 1 of R in general, of V, yeah? Because you didn't add new countable subsets of it. Okay. So
just to ensure, by P, we mean again here, call omega 1 R by the forcing P.
This parsing was the first poset I said. So it's the collapse omega, call omega 1 R, but then it also had this follow by adding a coin subset to omega 2. That portion is irrelevant. So you can just really think of it as, because why is it irrelevant? Because once you allotted the reals, then the other one is omega 2 closed, right? So it doesn't add new subsets of omega 1 anymore. And so we just need to really analyze the extension in which you obtain by call omega 1 R. So you can think of P as call omega 1 R, right? Actually, let me make that note here. So we now think of P as add 1 omega 2 is omega 1 omega 2 closed in V called. So it doesn't add new subsets of omega 1. And so it's just enough to analyze this extension. All right, so let now characterization of clubs in VP. This is the important thing here. Remember, suppose is a P name. P name for a subset of P omega 1 of R. And P is a condition in P. Right? So then the following are equivalent. One, P forces that S contains a club. And now again, it's in the sense of being closed under functions, under some Skolem functions, right?
Sure,
So there would be
Gregor, what's A contained in? What's little a? Oh, for a subset, okay. I thought,
is a P name for
yeah,
yeah. Yeah. That's why I hate articles. 1, 2. So P forces S contains a club, and we are using the notion of club like closed under finitely functions. Or for a club of sigma, now this is in V already, yeah? For I mean the other one is also in V, so no point of writing it. For a club of sigma, or for measure one. By the way, whatever we've done would just work through if you had any other measure on P omega 1R. It doesn't, any other supercompactness. So if your supercompactness filter, ultra filter was not the club filter, then you will just have for almost all sigma relative to that ultra filter, right? So it's not specific to the clubs here. For a club of sigma, for a comega many, or omega many G in Q and so I want to say Q sigma G, and then I will explain what that means. Or let me just write the notation we used in our paper. So for many, the thing is, why is it difficult for me to write? Because I have G, which is generic over this collapse on sigma to be countable, but I want to talk about P when P was a different forcing. So I want to say, I really want to say for a omega many G subset of P, not subset of this. But the way to say it is that for a club of sigma, for a omega many G, G forces, but in P, G is not a condition in P, so this is abuse of notation. P forces that sigma is in S dot. And now let me explain what this means. Where P forces P if and only if for every Q um, sorry, what did I do? So for club of sigma, for a omega many um, I think yes, I cannot say. Yeah, sorry. Maybe the best way to say it is just to say the thing and then no, okay, there's no space there for omega many. Um, yeah, P sigma, P intersection sigma. G G forces that sigma is in S. Sorry. Well, to okay. G is a filter. And union G versus sigma is this. Okay, so if it's a filter, remember our forcing is called omega 1 sigma, right? So those are countable sequences of reals. Sigma contains many of those things. Okay, so I want to look at only the, so if you pick a G which is filter over that, which would mean these three sequences have to line up, right? If G is a filter, then one sequence extend inside it, one sequence extends the other, which means now you can take a union. Why can you take the union? Well, because P was countably closed, right? So you can take the union and ask if the union forces this. Does this make sense? Guys, does it make sense? Can you hear me?
Sure. Why do you
Oh,
why do you take union?
why do
Like
I
if
take the union? Because G is not a
Hmm.
condition. G is
Hmm.
a subset of the poset.
Okay, but formally call omega 1 of R contains of functions.
okay,
Yes,
sorry.
but if I say it's a filter, that would mean they line up. Yeah. So you look. So I can take the union. It becomes one function long.
Aha. Aha, it's okay, we treat it as a function.
Yes. But why does it make sense to say omega many? Well, because the cardinality of that poset is the same as sigma. It's the cardinality of sigma. So it's the concept of being omega makes sense, right? It's still in a, I mean, concept of omega makes sense in general, but we are still in a Bayer space. That's what I mean. Okay. All right. So what we want to prove, I don't think we will have time to finish it. But what we want to prove is this nice characterization. If that something becomes contains a club, if for a club of sigma for a omega many G, G is going to force that sigma belongs to S. Okay, so let's try one direction, which I think is a little bit easier. So let's suppose P forces that S contains a club. Okay. Now we take that so just trying to see, maybe it's 2 to 1, that's easy. I think it's 2 to 1, that's easy. Yes. Oops. Suppose those 2 holds. Okay, what that means is that we have for a club of sigma in P omega 1 of R, for omega many. P forces sigma dot is in S dot, right? Want to see that P forces S contains a club. Oh, sorry, the other one was easy. Ah, it was the other one that was. This is the case where we have to use universal bareness. So 1 to 2. The P forces S contains a club. Right, now let F be a function from be a name. I mean, first that P forces the closure points of F are contained in S, right? Now we look for consider, let's say sigma is closed on the F, right? So we want to say when is sigma closed under F? Well, it's closed if every Q that you see, every condition you see in sigma, the value of and every condition in a real, then it forces a value for on the F if for every T in sigma, the set of Q in sigma intersection P such that Q forces Q decides the value of F, right? So there is a X in sigma such that Q forces F dot T is X is dense below P. So what does this mean? So that means every T you take in sigma, right? And just knowing the conditions in sigma, you can decide F of T already, right? For any condition, the dense many conditions in sigma would already decide the value of F. Okay, so set of such sigma is obviously club. The set of such sigma is a club. Because, right, because any substructure of, is this obvious to you that this is a club? Suppose it wasn't a club, right? Then you could by club, remember club here means measure 1 by this normal measure. So if it wasn't club, then there would be a T for which this set is not dense, but then you can fix the T, right? So, right, suppose not. By normality of mu, right? Remember, club means having measure 1 by according to Solovay measure, right? So by normality of mu, there is a fixed T such that for a club of sigma, the set of Q's here, such that for every X in sigma, Q doesn't force. Basically, you want to say that this set is non-dense, right? So the set of Q such that there exists X in sigma, such that Q forces F of T is X, is not dense below T. So by normality, you can fix the T for the bed T. Now, not dense means there is a condition which cannot be extended to such a thing, right? So that basically for that condition, all of its extensions do not force a value for it, right? So applying normality again, right? Can find some R below P such that for a club of sigma, the set there is no Q in sigma with and X in sigma such that Q forces F of T equals X. Okay, but this is total nonsense. There is a Q that decides the value F of T, right? So now you just pick that Q and put it to sigma. But this is contradiction because there is such a Q in general. So the set of such sigma must be mu measure 1 by fineness, right? Fine. Because there is one Q, pick your R, there is a Q that's going to force a value for F of T. All we want to do is take that Q and take that value and add it to sigma. But by fineness, the set of sigmas that contain that particular Q and that particular X is measure 1. So that's why. Okay. Was it clear?
Sir Grigor, when you write CL of F, do you mean, is this the notation for this
Closure of F. This is the set of all sigma such that F that are closed under F, basically. Okay, so what did we now have? So we now have that the set of sigma with this property such that for any T in sigma, the set of Q which give a value to F of T inside sigma is dense below P. Yeah. Okay, but now if you just intersect those dense sets, that would be your Omega many G's, right? So we have that for a club of sigma, the following calls. For each t, sorry, for club of sigma, dt, and for every, for club of sigma, for any ti peak inside sigma, the set, right, the set of conditions that decide the value for t, so the set of conditions in P intersection sigma, such that there is a value which force a value for ft from sigma, right? So the set of conditions that force the value of f at t belongs to sigma is dense. Below P. But now if you intersect, you get a comic set of generics. So if G belongs to the intersection of dt, then I should put sigma here, right? Then G has the property that I want. Then G forces sigma belongs to S dot. Right? Because G forces that sigma is closed under F. Because G forces sigma is a closure point of F. Why is this? Because for every value inside sigma, f dot t is forced to be inside sigma, right? So you have it. Okay, so but the set of such G's is comiga because you're intersecting dense open sets. Okay, so we have, so for a club of sigma, the set of G subset P intersection sigma such that G forces sigma check belongs to S dot is comica.
I'm somehow confused here. I thought that the sets D are sets of conditions. Can you scroll
Yes.
up to the D T sigma definition?
Yeah, so that's what I was trying to explain at the beginning, that this concept of comica makes sense regardless of which space I go in. What does comica mean in a topological space? It means to be intersection of dense open sets, right?
And what is the intersection over? Can you maybe specify? You intersect
The
over all
T comes from sigma, right? So this is T in
over all
sigma.
T's, right?
Yeah.
And do you then mean G is a subset of this intersection?
Oh, sorry, I meant if G intersects, all of them. So
Yeah.
I meant if G is a filter which intersects all of them. Sorry. You're right. You should think of it. You're right. This is not what I meant.
Thanks.
If G is a filter, such that G intersects dt sigma for every t in sigma. But what I wrote doesn't even make sense, right? You have to look at the set of G's which contain, whose initial segment belongs to the set of G's that intersect each one of those. That's a comic set. Because these are dense sets in the condition space.
Yeah, sure.
Mm-hmm. Oh, intersection is not empty.
So okay. So your sigma is fixed, and now for each dt you look at all the G's
which are generic for these particular dense sets.
Which yeah, and for each single T, you get a dense open set of G's, and that's why there's omega many G's. Is that right?
Mhm.
Okay.
Yes,
Okay.
could be dense open here.
No, I think you want that the set of G's is dense open, right? The
No,
set-
but this is dense open in the forcing sense. This d sigma t is dense open below p in the forcing sense, which, and now if you now look at the set of G's, generic G's, which intersect every one of these dense sets, that's omega.
I
in
guess I
relevant
see
context.
what you mean. Okay.
Yeah. Sorry, it's really my fault. So I hope the proof made sense. And we can just go over it again and stop, do the next one next time. So we have an S that contains a club. What we want to prove is that if a S contains a club, then I can find countable club of sigma in. This should be a member, right? We want to find a club of countable sets of reals such that for a omega many G, right? So generic filters, G will force that sigma belongs to S. Okay, but G is not a condition. What we really mean is that union G will force that. So this condition will force that, which is a condition in P. Okay. So let's start with S being a club, containing club, and so we take the club that it contains. Now we notice that we observe that if because the Salovey's measure is super compactness measure is normal fine, we have that for measure one many sigma, you will decide the value of f within sigma, basically, right? Usually what could happen is that you have a t, but to decide what f of t is, you need to go out of sigma. But here we're looking at all those sigma such that f of t is decided within sigma. Okay. So the dense many conditions that decide exactly what f dot t should be within sigma. Okay, so then we intersect those dense sets. I mean, we get a generic that intersects all of these dense sets, and the set of such generics is of course omega. But each generic which intersects all of these dense sets decides the value of f, right? Which within sigma decides the value of f within sigma, which means sigma is closed under f. And that means that G forces that sigma is in S. Okay, so let me stop the recording, and that's it for this time. Next time we'll prove the other way, and I hope maybe 2 more lectures and we will be done by this with this proof. And hopefully, I don't know what I will do next because we have 3 students here, and I want to do stuff for them. So I don't know what the topic after this will be. We have to think about this. Okay, guys.
A quick last question. You probably said
Yeah.
this, but what was the topology you used on the space of subsets of sigma? Like you have
Well,
this
you have to,
section sigma, like the G is a subset.
yes. So you have to.
Is it like stone space? Is that the
No, I would actually just go with 2 Bayer space. So the way I would do it is you just look at the enumerations of sigma itself, which gives you an enumeration of G, right? So that's how I would just look at countable sequences. So I would think of G as just a countable sequence of conditions. That's how I would do it.
It's, I guess, okay.
That's like what we were doing in the previous case. You can think of 2
Are you
generics.
fixed?
One generic enumerates the sigma, the next generic enumerates, tells you exactly what the conditions in G should be in. So one sequence will enumerate sigma, the other sequence will enumerate the points which should be in P. So you can think of a product topology of some kind. Right? Does it make sense, Lucas?
It will make sense, sure.
We can talk about this next time more. I wanted to do it.
And yeah, as soon as
Right.
as soon as you have an enumeration of sigma fixed, then
Yes.
increasing sequences through this space looks like sparse space. I agree.
Exactly. So
Okay.
you can think of pairs. And you also have a surjection, right? From sigma to, in fact, you could, yeah.
And this was the theorem where you used a push forward, right? Because
In the next part. In the next
Oh.
part we will use it. Not now.
But now you also
Proving-
used the measure on P instead of R. But maybe is this in bijection?
Use it? I'm not really sure if we are using the measure on sigma, but you don't really need the measure on P yet.
But what were the elements? What were the elements of P?
P is the poset of call omega 1 sigma, right? So it's countable
Yeah, but
sequences of reals.
this has a copy of omega 1 inside, right? So
Well, I mean, conditions are
inject-
just countable.
you can inject omega 1 into the poset, right?
Yes, but the poset
Inject
is
omega 1 into the reals.
but the conditions themselves are countable.
Yeah, but
Right.
I'm saying you have a surjection from R to the poset, but it's not in bijection with R in the poset.
No, it's not the bijection. No.
But you're using the measure on the poset, right? On the
But why are we using
counter.
because I'm enumerating sigma, so P intersection sigma gets enumerated as a subspace or something. So you don't really need to enumerate P, I think.
And not enumerate P, but
You can say something like for omega many enumerations of sigma, the corresponding G forces this for omega many.
But if sigma just contains reals, right? If sigma was just a countable set of reals.
But it is just countable set of reals.
But then in what sense can you intersect it with the poset?
This is what you mean. Well, the codes, right? So you could look at the set of.
Yes, but that's what I mean. So there you're pushing forward the measure, right? Because
but I don't need to really push.
I think it's probably the same as pushing forward the measure if you're like doing the calculation. Maybe I'm wrong, but
I don't really think you need to do that. Well, I mean, in some sense, you need the surjection. Yes.
Yes.
To talk about what the generics will. But yes. I don't think you need the measure on the because you can just, if you have the surjection, it tells you exactly what conditions you talk about. You just, in this stage, you only need to talk about that there is some way of getting a condition associated to sigma, right? Which decides for omega many enumerations of sigma, I can find a condition in P which does something. That's what this direction is saying. This should think of this lemma as saying that for a club of sigma, I can find omega many generics that enumerate sigma, from which if I extract the condition, which you can, because now you have actual enumeration of these 10 sets. Now you have fix an enumeration of sigma, then you fix an enumeration of these 10 sets in length omega, and you intersect them one by one, the way you usually prove Bayer category theorem. So if each enumeration of sigma gives you a canonical generic G, and then that's the G that we talk about. So it's not really, you don't really need, I think, to talk about the enumeration of P. But in the other direction, you do. Okay, I'm never gonna satisfy Lucas.
No, I'm sorry. I'm satisfied. I think I see that.
Yeah.
Yeah,
But in the
you
other
can-
direction, you're right. This is more serious. And I also think that this part is actually very confusing. Maybe we should do it again. If you look at the Obrat's notes and the paper that we wrote, I think it's quite confusing. It's like both of them, one does too much, the other one does too little. Yeah. Okay. So we meet next time. Okay.
Thanks.
All right. Ciao, guys.
Thanks, Rigor. See you next time.
See
See
you.
you.